Welcome back, folks, and this is going to be part 2 of our PCBWay sponsored Class A amplifier project. We've got the boards in, and I went with red this time because why not? It's fun. And yeah, the nice boards as usual. 5 boards for $5. Can't go wrong. So I got all the parts laid out here. Now, one of the things I had to do is I did not have 820 ohm resistors around. I thought I did, but they were surface mount, and I used through hole components in the PCB. So what I was able to do is make up 820 ohms by combining 2 resistors together. That'll work fine. It's just it's not as pretty, but it'll work fine. I did have the 180 ohm resistors though, and all the other values are there as well, so I have no problem. Here's my transistors, my capacitors, I got my solder, and my iron is all warmed up and ready to go. So let's get started with this build, and as usual, if something really weird happens, we'll stop at that point and mention it. But I think this is about the weirdest thing. I'm excited about this. It's been a couple of decades at least since I've actually designed a Class A amplifier. Having moved mostly over to digital, into small 8-bit computers and stuff like that for my hobby, I kind of left behind the whole linear world a little bit. And so this is my first true design for a Class A amplifier in a couple of decades. So we'll see if I remember what to do here. Anyway, let's get started. We'll see you at the end. I built up 2 of them because I wanted to try and put one in series with the other to get 2 stages of amplification to see how that works. And here I didn't use the input capacitor because if we're going to be linking these together, 2 capacitors in series actually reduces the capacitance. And since we already have a coupling capacitor on the output of this, we don't need one on the input of this. So in order to maintain bandwidth, I left that one out. So okay, well they're all hooked up, and they look like they're all okay. But let's hook them up to some power and put them on a scope, put a signal into them, and see what we get out of them. Okay, let me set up for that. Okay, so here we are. We're all hooked up. I've got the power supply going into it. We've got 10 volts reading on the power supply, and the power supply is telling me the circuit is drawing about 1 milliamp, which is what we expect. Now let's make sure that 10 volts is getting down here. It is. Now we can check the base voltage, which is supposed to be 1.8 volts. 1.79. So far we're doing pretty good. Now the emitter voltage should be about 1.1. Yeah, that's pretty good. And our collector voltage should be about 6 volts. So yeah, I think within the tolerances of the parts we're right on. Alright, now we got our DC measurements out of the way. Let's see if we can't put a signal into this thing. Okay, folks, we seem to have recovered after that power failure. It went on for quite a while. So anyway, this is the next day, and we now have our Class A amplifier all hooked up. We've got a signal coming in from the function generator. So we're going to put in 1 kilohertz. We'll do all this at 1 kilohertz. And we've got our 10 volts coming in here, and we've got an oscilloscope on the output. So let's have a look and see what we've got there. Now right here, you'll see at the top here, that's our output. And we got 6.067 volts coming out and 1.76 volts going in. Look at that waveform. I mean, that's a nice waveform. We don't have a lot of gain. So let's do that gain calculation. So we have 6.067 divided by 1. It's oscillating back and forth. We'll make it 1.75. That gives us about 3.46, 3.47, and we calculated when we did the theory on this. We calculated the gain would come out to 3.5 when we have the full 1K in the emitter. So we don't have any capacitors bypassing the AC here, and our gain is calculated as 3.5, and that's exactly what we're seeing here. But I want you guys to note the beautiful waveform. Like, that is a really nice sine wave. Very, very, very little distortion here. It's inverted. That's another thing you should note. It was 180 degrees phase inversion with this type of amplifier, with this common emitter Class A amplifier. And if we let's see if we can have a look at the fast Fourier transform. Let's see if it makes any sense to us. Hold on, we'll have to change the time base a little bit so we can get a lot of samples. Yeah, here we go. So we've got our peak at 3.3 dBm, and our first harmonic is down 46 dBm from that, and all the other ones are down minus 60 dBm, and we've got another one here at minus 48 dBm, so that's down 51 dB. So we're looking at here about less than 0.01% distortion, total harmonic distortion. That's pretty good. That's pretty good. So let's go ahead and we'll look at the amplifier using full bypass mode, so that the emitter resistor is completely bypassed. We're going to put on the jumper here. We're going to bypass the emitter for AC to ground, so that now what the amplifier will see for AC is basically just the internal resistance of the emitter. And as we saw before, like when we calculated that internal resistance about 22.7 ohms. So in this bypass mode, the gain is going to be 36K divided by 22.7, or about 159. So let's have a look at that. We're down now to 50 millivolts. We still want about a 6-volt output. There we go. I want to compare them all at about 6 volts peak to peak out. All right, so it looks like we have going in. Now this is measuring down here a little bit incorrectly, I guess, because there's some noise. If we were to increase the resolution on that, we're probably picking up a little bit of noise from the lab here, which is skewing that. That's better there. 50 millivolts, which is what the signal generator is saying. No, the signal generator is saying 40 millivolts. So we'll use the signal generator's output, because you can see that the fuzziness here from the noise that we're picking up, probably from all the LED lamps. And we got our 6 volts peak to peak out. So doing the math on that, we have 6 volts divided by 40 millivolts gives us a gain of 150. That's pretty close to what we calculated at 159. But now look at the waveform there. I mean, this is very distorted compared to what we saw before. And mind you, we do all that wonderful gain. We have a gain of 150, but we also got a lot of distortion. And let's bring in that math analysis again. Look at the Fourier transform of this and see what the harmonics look like. Oh, see. Okay. Now the output again is around, we've got 2.5 dBm or 2.6 dBm, but the first harmonic is down. It's only 14 dB down, so that's a 16 dB, and the second harmonic is down to about minus 35. So maybe we can ignore that. Well, you could add up all these here. Let's increase the time base here so we can get a little bit more in the window as we did before. Yeah, so that's quite a bit of distortion. Let me bring up a little calculator here and I'll try to figure it out. Sorry, we had a little interruption there. Somebody came to the door. Okay, so we're trying to calculate what that distortion works out to. So that, if you take all the peaks into account and kind of add them up, I mean that third peak is still significant. You're talking around about 3 to 4% total harmonic distortion, which is not considered acceptable for any kind of reasonable audio work. Okay, so now what we're going to do is we're going to try the amplifier in the swamped emitter mode, and that's where we leave a little bit of resistance in the emitter here for DC resistance. That's also AC resistance, so we'll only bypass from this point down. So we're bypassing the 820. So at this point here at E2, that'll become a virtual ground for AC, and we'll still be able to see 180 ohms in the AC side of things, the AC model. As we calculated before, we get 22.7 plus your 180 divided into 3.6K, which is the collector resistor. We get a gain of around about 18. So that's what we're looking for, to see if we can meet prediction. And so let's move this down, then adjust the input to get 6 volts peak to peak out. Now we can reduce the input a little bit. Okay, there we can see that we've got 367 millivolts going in and 6.067 volts coming out, and we've still got a very nice looking waveform. Okay, so now we're about minus 30 dB, and all these little ones down here are not going to add up to very much. Let me go and do the calculation on this. This one's going to be pretty tough. So about minus 31.4. I'll go calculate this. Okay. So taking these two into account, we're looking now at about 0.07% total harmonic distortion, which it ain't bad. We can see now we have like a compromise between gain and distortion. Let's turn that off for now. And look at that gain. So we've got 6.13. The generator is saying 340 millivolts peak to peak. So I'm going to take its word for it, because again, we could be picking up a little bit of noise. And that gives us a gain of 17.8, and we calculated 18. So yeah, we're well within the tolerances of the components. So all this theory actually works out. It's good to learn some of this. Now, like I said in the previous video, get yourself some good textbooks on it. I'll put some names down in the description. And look up some of this theory, because if you're going to do any kind of design work at all, or be able to do any kind of troubleshooting, you need to know some of this stuff. Anyway, what I'm going to do is I'm going to combine these two together. Both of them I'm going to have in swamped emitter mode. Now, what would you expect the gain to be if we do that? We might say, oh, it's 18 times 18, which is going to be 324, but that's not quite right. The reason for that is, okay, the input stage of this amplifier here has got a 10K in parallel with a 2.2K from the perspective of AC. So when you do that calculation, you end up that the input impedance of this is about 1.8K. And if you look at the output impedance, of course the output impedance is just the collector resistor, so that's 3.6K. And if you do the math there, you end up with a attenuation between the two amplifiers of 0.33. Now, so if we get that 0.33 and we multiply that by the 324, we get a figure of about 108. So let's do this and see if we're right. Let's hook all this up, and we'll find out. Okay, let's turn that power back on. We're going to have to reduce the input, of course. Going to be clipping like mad. And let's reduce that input down until we get roughly 6 volts out. So okay, looks like we got a really nice, really sweet waveform there. And we have 6 volts out, precisely 6 volts out, and we have, according to the function generator, we've got 58 millivolts going in. So let's see what gain that is. That's a gain of 103.5 roughly. So yeah, we weren't far off with that 108. That's pretty good. Let's see what our distortion looks like now. Let's see what we got there now for total harmonic distortion. Okay, so this is coming out to about 0.063% total harmonic distortion, which is not bad at all. An audio amplifier is considered fairly good if it's got less than 0.1% total harmonic distortion. So we're down to around about half of that. Okay guys, I'm going to wrap this up now. I think we've done a nice job here, and I'd like to thank PCBWay again for helping me out with this. They're a great partner, and they do such a great job of it too. So if you have a little design that you want to have built up, get them to make up those supports for you. You'll be really happy with it. Thank you for joining me. Leave a like if you want. Please subscribe, and I've put a little link down there if you want to help out the channel. You can through PayPal. All right, see you in the next one. Bye bye.